Hi everyone and welcome to my YouTube channel. So in this video we'll be discussing the BMO1, which is the British Mathematical Olympiad Round 1, which was held in 2023 last year. Basically we'll be solving the 6 problems one by one in each video. So in this video we'll be just solving problem 1, and I'm going to be uploading the next videos one by one. Each video is going to contain one problem. So first of all, let's talk a little about the BMO1. So first of all, if you want to apply to like the Math Olympiad team in the UK, then first of all you need to do a regional Math Olympiad, which is like the SMC, the Senior Math Challenge, which is a multiple choice exam. Then after you qualify basically for the BMO1, which is basically a set of 6 problems. So you've got the time allowed is 3.5 hours, and of course this is not a multiple choice test, but it is a written proof exam. You have 6 problems, each one is worth 10 points, so the total mark is just 60. So as you can see, we have got like here an instruction paper in which they simply stress that full written solutions are required, and one complete solution is better than partials here and there. Of course, this is a very important thing in Math Olympiad. Like it's better to focus on one problem and finish it for sure, making sure that you get 10 out of 10. This is better than just reading all the problems and doing like some steps here and there, because usually you don't get a lot if you take partials here and there. So it's better to focus on one problem and solve it, make sure you solve it, than taking partials here and there. So this is just the stress on that. Yeah, the rest is just technical stuff. Of course, after you do the BMO1, you qualify to the BMO2, which is a set of 4 problems. Of course, they are way more difficult than these problems here. And after you qualify there, I think you qualify to some camp, and like you've got some training, and then they of course do the TST, the team selection test. Like they have some criteria for that in the camp, and some tests, I think. So after that, of course, the team is decided, and the 6 students go for sure for some training and then go to the IMO. So right now in this video we'll be just solving problem 1 in the BMO1 paper for 2023. So I hope you guys are excited, and what are we waiting for? Let's get started. Alright, so before we started with the problem 1, the UKMT team has done a very good job of posting video solutions for each one of these problems. In fact, they are very organized, that you can find the video solutions for all the papers for BMO1, and for each problem you've got one video for that. So you can of course check these videos as well. But here, of course, I'm going just to be posting here explaining my solution. So it's always better to, have many flavors and many solutions for these problems. Okay, so let's start with the problem 1. So as we can see here, we've got for sure a combinatorics problem. Whenever you see some lengthy problem, then it's just combinatorics. Okay, so let's get started. Here they are telling us that we've got an unreliable typist that can guarantee when they try to type a word with different letters, every letter of the word will appear exactly once in what they type, and each letter will occur at most 1 letter late. So what does that mean? For example, let's say we've got the word math. So here when you're going to write this letter, you know that each letter is going to appear once. So M will appear only once. You cannot have two M's, for example. The same thing for A, T, H, and S. This is what the first thing like means. Here appears exactly once. Then they are telling us that it appears at most one letter late. So that means that this M here is not necessarily the first letter. It might become the second letter, and here something precedes it. But it can never be two letters late. It can only be either like here. So for example, this is number 1. It can either go to 1 or it can go to 2. But it cannot go to 3, 4, or like more than that. Okay. Next thing, they are telling us, okay, each letter will occur at most one letter late. But of course here they're saying it may occur more than one letter early. So for example, this letter H, right now its order is 4. So it can go for 4 or 5, of course, right now. But in fact, it can go before that. So it can go actually to 3 or to 2 or to 1. So in fact, as you can see, it can go late at most by 1, but it can go early like with no conditions at all. Okay. And now, for example, they are giving us this example, maths. So we might write the same maths by preserving everything. For example, here M goes to M, A goes to A, like they preserved everything. Or we can get this one. How do we get this one? Well, first of all, you can see that M is preserved. So it's 1 and it's still 1. But now, A, what happened to A? It was 2 here, but now it became 3. Of course, this is legal because it went at most by 1. It went exactly by 1 late. Okay, but now for the T, what happened to the T? It was number 3. Now it became number 2. As you said, we don't have any conditions if it went early, because it can go as early as it wants, no problem. Then we look for H. So H and S are preserved, 4 and 5, they're 4 and 5, no problem. Next, T, M, A, S, H. How do we get this? First of all, let's look for M. M was number 1, now it became number 2. This is legal. A is number 2, it became number 3, legal. T was number 3, it became number 1, also legal. Now H was number 4, it became number 5, so this is legal. And finally S was number 5, it became number 4, this is also legal. But we cannot get this one. Why we cannot get this one? ATMSH. Well, let's see. M was number 1. Now it became number 3. So now it's late by not at most 1. Now it's late by 2, which is illegal. Alright, so now we understand what is this process. They are telling us determine with proof the number of possible spellings of Olympiads that might be typed. So we need just to catch this word and try to count all the possible ways by applying these processes. Okay, first of all, of course, we should look at this word and notice that all the letters are different, which is like very good. So we should not worry about having the same letters. So actually, do we really care about the letters? For example, this is O or this is L? No. So we can just replace them, for example, with numbers if we want. So right now, Olympiads is how many letters? Let's see. Only 3 and 3 and 3. Okay, so it's 9. So basically, we can just now think about it like in terms of f of 9. So we can simply define a function, something like this. We can define f of n to be the number like for n strings, or like let's say string of n or of length n, the number of possible ways to represent it. And now, of course, now the question is just find f of 9. What is f of 9? Well, let's try to find f of 1, f of 2, and these small numbers first. Maybe they might help us, or maybe we can see a pattern or something. So let's try finding, first of all, f of 1. So what does f of 1 represent? It represents the number of ways if we just have a string of length 1. So if we just have, let's say, the letter A. Of course, now it's 1 for sure. There is only one way, which is the same string. But let's say we have 2. What is f of 2? So let's say we have AB. Well, clearly we can either have AB or we can have BA. So now this was 1, 2. Now it became 2, 1. This is Lika. So it's 2. f of 2 is 2. What about f of 3? Well, if we have f of 3, then we need to, for example, take ABC, let's say, and think about it. We have ABC. Well, first of all, A. If we start like by order, A either goes, like right now it's the first one, so it's either the first of the new string or it's the second, right? So we actually have two possibilities. Let's think about it like this. It's either A and then we have two things, or it's A and we have something like that. Okay, so in this case here, if it was here, then actually now we're solving a smaller problem, a sub-problem, which is now we're solving it for f of 2. So in fact here, how many, like here, if we count now how many ways to do this, it's actually f of 2. So it's 2. Let's keep it f of 2 here. Okay, now we just need to count this branch. Okay, so for this branch actually, A went there. So now we look for B. Now B actually has two cases. B was number 2. So it either goes here or it goes here. So if B went here, then C is here, and if we like if B was here, then C is here, and actually we have 2. So that means actually we found f of 3 is the sum of f of 2 plus 2. So that means f of 3 is equal to f of 2 plus 2, which is simply 4. Alright, so right now let's look at them. F of 1 is 1, f of 2 is 2, and f of 3 is 4. 1, 2, 4. Okay, one guess is that for sure it's powers of 2 maybe. So let's check. Let's go for f of 4. If we want to f of 4, we're going to do something similar that we did with f of 3. As we said, let's go for A, B, C, D. First of all, A. A either goes first or second. So in the first case, now we're solving as like a smaller problem, which is f of 3. But in the later one, we have something like this. Now we need to discuss B. So B either goes here or goes here. Let's think about it. We need to make two branches here. So the first one is B, A, this. The other one is A, B, this. Actually here, if you look at this one here, now we handle these two. Now C and D can play here. So actually now this is also a sub problem here. In fact, it's f of 2. Now we go here and solve this one. So now for C and D, now actually C either goes here or goes here. Well, actually you can think about it. If C goes here, or let's simply do branching here as well. So it's either C, A, B, something here, or it's A, B, C. Of course, each one of them is 1 here, because now it's only d. But you can think about it actually like this. This is f of 1, because we're just doing the same thing like we did here. So f of 1, it is 1, because we're just solving like one problem for this. And here in this case, it's actually 1, that it's d. So for example, here f of 4 is what? It's f of 3 plus f of 2 plus f of 1 plus 1. So let's write that recursion plus 1. Okay, we can of course find this one easily. It's 4 plus 2 plus 1 plus 1, which is 8. So for sure, of course, the answer like is 2 to the n. It's a power of 2. Okay, so we got now what is f of 4. It's 8. Of course, now we can easily prove that means the recursion f of n is equal to basically sigma f of I from I is going to, from 1 till n minus 1 plus 1. We can easily prove this by just doing this branching. So for example, you can just do this. Say the first letter A can either, like if it's like this, then this can be done in n minus 1, or if it's like this, then we also do 2 branches. If it's B, A, and stuff like this, then it can be done in f of n minus 1, n minus 2. Else, it's A, B, and stuff. Then we also do this one by doing also 2 branches. And we can continue for with this one. Like if C was here, then it's going to be f of n minus 3, or if C was there, and so on. So you can easily show we have this recursion. And now, my dear friends, the question is kind of solved, because once you find a recursion, then it's super easy to solve. So let's see how we can do that. By induction, like remember we have proven that, or we have a guess actually. What is f of I? Our guess is that f of I is equal to 2 to the I think minus 1. Okay, let's check. Yes, it's 2 to the I minus 1, because look at it, 2 to the 0 here, 2 to the 2 minus 1, so it's 2 here, 4, 2 to the 2 here, 2 to the 3. Yes, so this is actually our guess. This is our guess. So let's just prove it from the induction here, by induction. Of course, what is f of n? It's 2 to the 0 plus 2 to the 1 plus and so on. Let's find f of n. It's equal to 2 to the 0 plus 2 to the 1 plus 2 squared, and so on till 2 to the n minus 2 actually, because 2 to the n minus is 1 minus 1, then plus 1. Alright, this is equal to, of course, when you have something like this, this is a geometric series, and we have the simple sum, this, and then plus 1. This is, of course, you should know this one, super easy, like geometric series. If you want to add it, you just simply get 2 to the n minus 1 minus 1. Okay, sorry, I made a mistake here. It's minus 2, which is equal to 2 to the n minus 1, and basically we're done. We have shown that indeed it is true. And of course, now our goal was to find f of 9, so now it's just equal to 2 to the 8, and this is basically the answer. Of course, you can calculate this one. So it's over 4. Okay, actually this one is just 128, I think, times 2. Let me check. I think that was it. Of course, you should memorize the first powers of 2 till 10. But for me, I always forget these ones. So let me just check. Multiply this by 2. Okay, yes, that works. Alright, so simply this is the final answer, and we are done. Alright, so as a summary, this question requires us, of course, to try, like just like any standard combinatorics question, you need to simply go with small values and try to solve the problem for small values, play with it. First of all, of course, you need to understand the question for sure. After you understand it, you simply try to play with it for small values. So here we started with f of 1 is 1, f of 2 is 2. Then when we discussed f of 3, we noticed that we kind of have a recursion, because this thing here is like kind of f of 2. We're solving the sub-problem, and we went with that, f of 4, the same thing. So we noticed that we can easily get a recursive relation. And once we get this recursion, because how can we solve a recursion? Like the easiest way is simply, if you can guess the answer, then you can simply do induction after that. So this is exactly what we did here, and basically we found the answer and we substituted, and basically we are done. Alright, so in the next video we'll be solving problem 2. So I hope you guys enjoyed this video. Please like, share and subscribe to my channel, and see you guys in the next video.